So good morning, everyone. We're excited to be here in TLMS 2025, and thanks for joining my talk today on uncovering financial fraud with graph machine learning at scale. So about me, although I didn't know that there's this introduction, very thorough introduction, but in short, I'm Erfan. I'm a senior AI ML scientist at Vanguard, doing research, development, and deployment of large-scale models in production, especially for fraud detection, and with a main theme of graph machine learning. Earlier to that, I was a data scientist at TD Bank, and also I graduated from the University of Toronto here. So a little about what we do and who we are at Vanguard. So a lot of you may have already heard of Vanguard or used Vanguard products. Vanguard is one of the most largest companies in asset management across the globe. It offers investment management, advice, retirement services to tens of millions of clients all across the globe. So historically, Vanguard has had a bolder presence in the US than in Canada, but right now, Vanguard is also expanding its footprint in Canada with the AI research hub that it's building in Toronto and the partnership with the University of Toronto. So more exciting news coming out of Vanguard in the few years in Toronto on fundamental AI research. And I'm personally really looking forward to that. All right, so about today's talk. So first, I want to talk a little about how modern fraud is evolving, and especially in the finance sector. And then I'll touch a little bit on how more traditional fraud detection measures, including machine learning or rule-based models, fail to detect some of the modern trends in financial fraud. And then I'll talk about a little bit on how we can formulate this whole fraud detection problem as a graph problem, and then how we can approach this with graph machine learning models. And then I'll talk about more on how we deploy these systems in production, because there's a lot of ticks and trips into efficiently deploying these graph machine learning models at scale, especially if you're in a large financial firm that deals with millions of clients and customers. I'll talk about some key deployment considerations there and how we can make the systems more efficient. And finally, I briefly talk about the explainability side of the house and how we can make our models and systems more transparent. So financial fraud has been an ever-evolving problem of the financial companies. It can take many shapes and forms, like identity theft where a fraudster can hijack your personal information like social security number, your banking details, and commit fraud. The other very common way of doing fraud is synthetic identity fraud, where fraudsters get access to to some PII information, like bank account information, like your name, your social security number, things like that, from anywhere, like on dark web, anywhere. And then they start to mix those information together, phone number from someone, social security number from someone else, and come up with some synthetic identities, some fake identities, and start doing fraudulent things. They create new accounts in financial companies. They submit applications with those unreal identities, and then start to fraudulent activities. Money mules, which is pretty common pattern in money laundering in particular, and then account takeover, of course, one of the most common shapes of fraud, where fraudsters break into your account, take control of it, and then do unauthorized transactions. And then authorized push payment fraud, which they use social engineering techniques and make the victim willingly move money to their accounts or things like that. The list doesn't stop here. It goes on and on. But these are some of the major forms of financial fraud right now. And based on some report came out on 2024 by Allo Institution, based on the statistics of 2023, almost 60% of financial firms, including banks, fintechs, and credit unions, reported over 500K loss directly in fraud. This is a pretty important problem right now. That number is getting larger and larger every year. It's larger in 2024 than how it was in 2023. And the issue is so the fraudsters are getting smarter with the development of technology. There's very cool AI tools that we use, like, for example, to combat fraud. They also take advantage of that to get more sophisticated in their tactics. And it's kind of an adversarial game going on between the bad actors and the good actors trying to stop them. So one of the main issues with the more traditional methods, machine learning models, or just rule-based fraud detection measures, is that they often individual focused. So as I mentioned, one of the types of fraud is synthetic identity fraud, which normally happens in a massive attack wave. So in the sense that those fraudsters come up with thousands of synthetic identities, they all of a sudden start to hit financial institution in a very, very short amount of time. Like in a day, they submit 10,000 new account applications or start fraudulent transaction to overwhelm the more traditional measures or the human investigator that's taking care of investigation. So it's often coordinated fraud attacks rather than just individual isolated events. So in this case, traditional models, machine learning or non-machine learning models, often see fraudulent events individually, meaning that the fraudulent event comes in, they look at the different features that it has based on the historical patterns, and then at first sight, it might look like that the event is legitimate because, for example, the bank information is legitimate, the social security number is legitimate, but then when you put together the other fraud events that are happening at the same time, you realize that there is some sort of connection which makes this whole activity suspicious. For example, in this graph snapshot that I included for you here, you can see that multiple bad actors started to leverage same bank information or social security number, or could be IP addresses, email addresses, whatever. And then, although when looking at them in isolation, they look legitimate, this clustering around certain PII could be a suspicious, could be a red flag that something suspicious is going on. This big picture is something that more traditional models and measures fail to capture. But when you take all those information to graph or a network, so people use it interchangeably, network analysis, graph analysis, you immediately will be able to uncover those kind of relationships that are not very obvious just by looking at them individually. So that was on the importance of analyzing fraud in a network setup or in graph. But now I want to talk about a little on how we can formally take the fraud detection problem and take it onto the graph form. So it could be anything. This is just a generic example. It could be any data model that you use depending on your financial institution, type of PII, or interactions between the accounts. But as a generic example, assuming that the users are associated to certain PII, like bank account information, like IP addresses, the location they use to access their accounts, all those information could be represented in a format of a heterogeneous graph where each node represents a financial entity in your graph. You have your client or users nodes, which are connected or associated to the PII that they use in the format of other type of nodes in the graph. On top of that, you also want to model the interaction between your users or clients in the format of money transfer between accounts, money deposit, money withdrawal, and those are certain things that you can also represent in the format of specific nodes or edge in your graph. You can model it in a homogeneous graph depending on what your strategy is, but this is a pretty common strategy to model financial relationship in a heterogeneous graph. So this multi-entity modeling enables detection of shared infrastructure. Like if some user is using same IP address, same bank account, they get connected to each other. And that clustering, if it's going on, you'll be able to uncover it so fast. On top of these PII or associations, like interactions, I'd say, you can also enrich your graph with some information that goes into each node or edge or any graph entity in the format of properties or features in graph machine learning terminologies. Like in this example, I included account age, account balance, and so on and so forth, which can go into your nodes. Like in this case, it's profile node, but it could be any of those nodes in your graph, which you can further down the line use to train a model or do any modeling activities. These are something that we commonly call contextual features, but there's also possibility of enriching your graph entities with structural features that are coming out of your graph structure and shape. Like, for example, once you generated your graph, there are things like Louvain community or betweenness centrality or degree centrality or page rank that you can extract and also embed those into your nodes and edges, which we call structural features. So those will all go into your graph entities in the format of features that can be used down the line for training a model. So once you consolidated your data model and then enriched it with some of the features that you extract, either contextually or from the structure of your graph, you have many options now. You can use just simple supervised learning models in the sense that those features can all be fit into a classification head. Could be anything like a tabular model or XGBoost model, gradient boosting models, and even a simple MLP. You can get more fancy and, for example, use graph transformers as well. So you basically train your model, your classification head based on the previously known labels that you have in your organization, let's say, and then you have an end-to-end pipeline to generate risk scores for fraud events. Whether it could be transaction, could be application, could be a node, could be an edge, whatever that you want to classify in your graph. A pretty well-known issue in fraud detection, though, is label scarcity. Well, especially if you're dealing with all of a sudden a new type of fraud, which you hadn't dealt with in your organization, you end up having not enough data to train a supervised model. So that's where you can take advantage of some unsupervised anomaly detection models. So you can take a graph autoencoder, could be any GNN that you could use, and then to generate some sort of latent space based on your initially generated features, and then you can use reconstruction score as a measure of your events being anomalous. So you can take advantage of node-to-vec, pretty simple, more advanced graph autoencoders, or more hybrid approaches like dominant, which I depicted in the picture at the middle. You take a graph encoder, latent space, and you reconstruct the both structural and contextual features, and you'll have anomaly scores, let's say, for all of your profiles in this case. Also, you can take advantage of semi-supervised methods. Use message passing, for example, or just manual label propagation in the sense that closeness to any previously known fraud could go into your features and then later used to train a model or something like that. Or you can take advantage of graph convolutional network, graph sage, or a graph attention network. Depending on your application, some of these methods are preferable over others. We'll get back to it in a few slides. So getting into the deployment, assuming that you already chose your machine learning approach that you want to take now, you trained it, whatever, now you want to deploy it in production. There are several considerations that you may need to take into account. So everything starts with where you ingest the data. So in finance sector, your features will always be in the format of real-time and non-real-time features. So some of the information like transactions, login activities, bank services, deposit, money withdrawal, these things are often need to be ingested and processed in real-time manner. Some of the information not necessarily need to be ingested in real time. Those are like historical aggregation of some behavioral features of your clients, things like that, things that change less often. So you want to set up different processing tools or methods to be able to ingest both types of those data. Real-time, use something like Kafka or other data streaming technologies or Spark. And then everything now will go into a graph database, which in my opinion is the core to this whole ecosystem. So if you have a proper graph database, which is optimized, which is maintained in a well manner, that's the core and the key to the success of this whole methodology. So there are several graph databases out there. Some of them are more managed, fully managed by the company. Some of them are less fully managed. You have to take care of the ingestions or integration of downstream models with those. So I'm not allowed to name a company, but there are quite a few companies out there providing graph databases services. So this very huge, large graph that you stored in the graph database is a dynamic graph. It could be tens of millions of nodes to properly represent all the information for clients of a large financial firm. It changes in real time, new nodes getting added, things like that. So you want to set up feature stores to store graph embeddings as well as feature layers that represent the behavior of your nodes and edges and every entity that you have in the graph. Those features are used in offline manner or in online manner for training and inference, respectively. So it's not that you necessarily have to do inference in real time. You have the option of doing it in batch mode in real time. We'll talk about it in a little bit. But then it will be integrated with some monitoring, evaluation, and alarming system, and also some case management tool for your end users to be able to interact with the predictions or outcomes of your model, which is also necessary in this architecture. So let's talk a little bit about some of the key considerations in this deployment and this workflow that we just talked about. So as I briefly touched on, the choice of real-time versus batch mode inference comes with a trade-off, of course. So real-time inference will help you be on the preventive side rather than on the detection side. So if you deploy in real time, you prevent your transaction from getting finalized. You prevent the application from getting in. That's good, but that comes with the issue of, because you don't want to have a high latency. You don't want to get your user waiting for a couple of minutes before they want to log into their accounts or anything like that. So you end up using some features that are not as complicated or as rich. So in this case, you may want to take advantage of those feature stores that I talked about. So we have offline feature stores, online feature stores. We can take advantage of online feature stores to pre-compute some of those features and then use the pre-computed features during the inference, though there's always a lag. So those pre-computed features, they do not always represent the graph structure or features that are coming from the latest graph structure, because there's always a lag between refreshing those features. But sometimes you may just want to estimate some of the features that you are using in real-time deployment. So you can switch to inference. You can use very, very complicated and time-consuming features, but that comes with the issue of being a little bit behind of the bad actors doing fraudulent stuff. So one of the common practices that companies do is that they take advantage of a hybrid approach. So they have lighter version of the models at the forefront and doing in real time. And then there are some batch mode models that are running overnight and then detecting some of those that are getting away from the real-time measures. So kind of a defense in-depth strategy for this. So when it comes to choosing the right model, some of the models we discussed, it's important for you to go to the models that have inductive capabilities. So inductive learning in the sense that when new nodes or new edges are added to your graph, your models, your trained models can generalize beyond the unseen nodes. So if you use GCN, for example, you will end up, you will have to retrain your model when your graph changes. But GraphSage, for example, because it uses some sort of sampling, it can generalize beyond the unseen nodes, and you don't have to deal with that issue. So the graph ingestion also happens in a periodic or real time, depending on what features you are ingesting, and updating your graph with delta ingestion, and then that in turn triggers some feature calculation that I talked about to update your feature stores, whether it's offline or online feature store. And then it's also very important to have proper model monitoring, versioning, and registry to send to kind of keeping track of your models, metadata, hyperparameters, and things like that. It's also pretty important when you're going through a model upgrade. When you're upgrading your model, it lets you to run a shadow testing process by having the two models working in production at the same time. And then once you made sure of the performance enhancement, you do the final elevation. And then, of course, things like data distribution drift, label distribution, things like that, that we want to be careful about. So we need to have that monitoring part integrated so that when our graph features are changing significantly, we get notified about it. And then finally, I talked about having a case management tool, which we can use to let our end users interact with our model outputs, whether it's graph, whether it's subgraph snapshots or it's just some of the explanations that you generate for your model. That let you collect feedback from your end users and then use it down the line for retraining your model. Final slide. So it's all high-stake applications of machine learning and AI ML, especially in finance sector. It's well known that the model decision shouldn't just be accurate, it should be explainable. So if you're training a very complicated transformer-based model that generates very accurate scores, risk scores, and prevents fraud, if you have a hard time convincing your fraud investigation team on the rationale behind your model's prediction, you're not in a good spot. So when choosing your features, your model architecture, and everything, you need to be mindful about that. So in this approach of using GraphML for fraud detection, we have several layers of bringing explainability to the model. So it starts with the features themselves. So when I talked about some of the features that we extract from the graph structure, those are features that are inherently auditable and explainable. And then when you trace back the value of the final outcome of your model to those features, it should be something that the fraud investigators are comfortable with, that aligns with their intuition. Secondly, the structured reasoning via subgraph topologies itself. So even if your end users, the investigators, don't know how your model works, your GNN model works and everything like that, once you have the final outcome and then you'll provide them these snapshots, like one hop, two hop snapshots of your graph for the entity of interest, they can go through it with their intuition. So for example, in this case, on the top right, you can see that yellow new account, which was going to be created, which was submitting an application or something like that. Then we realized that that account is associated to 6 different bank accounts, which were previously used by some other bad actors. They were compromised bank accounts, and it doesn't stop at one hub. This picture is a one hub, but it can extend to 2 hub and 3 hub. It gets more and more complicated, so you gotta strike a good balance between the intuition behind these and how intuitive these snapshots could be for your investigators. And finally, on top of these, you can also always use things like SHAP values, like a GNN explainer, if you're going with the GNN option to kind of trace back the final outcome of your model to some of the features that you are using, which should be or better be in explainable themselves. All right, so let me summarize my talk very quickly. The most important point that I wanted to make in this presentation was that fraud is relational. So the modern attacks involve network, not just individuals, and that's where some of the traditional models fall short. Then graph modeling reveals some of those hidden patterns, and graph machine learning can complement that graph data model to automate this whole investigation process that the fraud investigators go through it. You can take advantage of supervised, unsupervised, and semi-supervised machine learning models. And then when it comes to real-world deployment, there are some tips and tricks, and you need to be thoughtful when designing your architecture depending on what you need to come out of your workflow and your pipeline. And finally, just explainability is essential, especially if you're working in finance, you want to be auditable, you can't just use a very dense representation of the features, trace back your final outcomes to that dense representation that fraud investigators are not really familiar with. Yeah, thank you very much. Hope that you found the content useful.
Thank you very much, Erfan. So do we have any questions on the floor? We'll have a mic runner come and run to you with a mic.
Thanks for your presentation. I'm curious about how much you're able to collaborate with other financial institutions to learn about the counterparties and transactions and to grow your graph database beyond what's available to Vanguard.
Right, so that's a very good question, actually. I would say it's an ongoing activity, not in Vanguard, but financial institutions are considering that. But because of some data privacy issues, they don't want to share the data in a one single graph database because they don't want to let other institutions know about the details of their. So what can be effectively used, or something that's being explored in that area, is federated learning, where each individual company has its own graph database. But then the features coming out of that graph database can be used in a federated learning manner to learn what are some graph-derived features that could be a good driver for identifying risky behavior. So that's as far as I know about it.
We have time for one last question.
Hey, thanks. That was really, really interesting. I think my question is more about the model side of things. So I'm assuming fraud detection is a super imbalanced class problem, right? Because I hope most transactions aren't fraudulent. So are there any specific, graph-related techniques to deal with this, or is it just, like the normal stuff like weighting, augmentation, et cetera?
Yeah, basically, how we actually deal with that data imbalance is at the feature level. So once we extracted those features out of the graph, we have the features that are obviously imbalanced, and then we take care of it with different imbalance techniques. But at the graph level, adding some sort of artificial nodes may induce some behaviors that are not really representative of the actual graph behavior. I wouldn't say that it can't be done, but at least we have to keep that in mind to not induce any relationship that it's not representative of actual data. But yeah, definitely using, and I've seen also some research and studies in using some generative models, generating models to generate 2-hub or 1-hub subgraphs that are following the same patterns of the known subgraphs that are being risky, and then use those to generate some features and deal with the data imbalance. But yeah, that was a very good question.